Okay, so for people joining this live stream, this is one of our live working sessions about physics and other things. And we have a number of people here, including an outside guest, Jeremy Avigad from Carnegie Mellon. And the subject that we want to talk about, I want to talk about at least, is the physicalization of metamathematics. Maybe I should give, at least for Jeremy's sake, a brief introduction to what on earth we're talking about, okay? So the basic point is we have done this big physics project, which is looking incredibly promising as providing an actual sort of underlying machine code for physics. And one of the things that is really remarkable and wonderful is that it seems that that underlying machine code for physics has a lot of commonality with the way that mathematics works, which is bizarre and interesting. And what does this mean? Well, one of the principal sort of subjects here are these things we call multi-way systems, which are just systems where you have rewrite rules and you're rewriting in all possible ways. So we can think of this as, here, if I share my screen, I could run one of these things. Let's say, let's just say we, let's take a typical multi-way system. And we got multi-way systems for all kinds of things. We got multi-way systems for combinators. We got multi-way systems for tic-tac-toe games, all kinds of stuff. But the one that let's just take one example. So let's just do one with strings. And we'll start off from just the string A and run it for 4 steps, let's say, and make a states graph. Okay, so what is this doing? This is making a graph. Jeremy probably understands what this is doing. This is just doing, it's applying that rule at every place that it can, and it's showing the various different outcomes you can get, right? So as in variously confused ways. So, okay, first thing is, how does this relate to physics? We are pretty sure that this is a good picture of what happens in quantum mechanics, and that in quantum mechanics, in the real case, we're not rewriting strings, but we're rewriting these hypergraphs that we think represent the structure of space, and the whole situation is a bit more complicated, but qualitatively, it's the same story. And the story of how the large scale limit of these hypergraphs work is the story of how general relativity arises, but the story of the large scale limit of these multi-way graphs is a story of how quantum mechanics arises. And basically what's happening is that these different blue things here can be thought of as different quantum states. And so this is time evolution going down the page. And then at any given step, there may be some collection of possible states. There are different ways to foliate this, different ways to assign time, but with any given way of assigning time, like the one where we're just taking successive layers here, we can define a thing we call a branchial graph. So I don't know whether this has come up in the sort of more theorem-proving type of world, but so that's a graph that shows the common ancestry of states here. So 2 states are joined by an edge when they have a common ancestor on the step before. Okay, so here I have to continue this one more step to see that case. Okay, so here we go. So this is now saying A, B, A, B, B. A, B, A, B, B has a common ancestor with A, B, B, A, B. Whatever it is there, that one there. So it's joined by an edge. So this picture we think is a map of essentially quantum entanglements between states. In the same way as in the space-time case, there's a corresponding map, which is kind of, the slice of this graph represents quantum entanglement space. The slice of the corresponding graph in space-time represents space. And there are a variety of different reference frames that you can use to look at this depending on how you choose to assign time. You can make any foliation of this multi-way graph that's consistent with the partial order defined by the actual evolution rules. So And then so a thing that we think is a big deal is whether these graphs, whether these rewrite rules are what we call causal invariant, which is basically a slight generalization of the notion of confluence. Okay, so in other words, does every branch subsequently come together? And why is that significant? Well, in a sense, that's actually the reason in the space-time case why we think relativity works, and in the quantum case, it's why we think there is a definite quantum objectivity, that there's an objective notion of what happens in quantum mechanics, because it's associated with, even though there are different microscopic paths that can be taken, kind of the overall all observers will agree about what's happening. And then in another piece of kind of term rewriting meets physics, Jonathan has had a kind of interpretation of quantum mechanics that basically says what an observer is doing in quantum mechanics is doing completions. So in other words, when an observer is saying, I'm going to decide that something definite has happened in the world, what they're doing is they're making an equivalence class of states that correspond to different things that they say are the same measurement. And to implement that equivalence class, they're essentially doing a completion by adding rules to the multi-way system. And I don't know, we should show Jonathan's recent thing about, just as an example of how this plays out. We can show an example here of, let's see, bulletins. Oh, it's still the latest bulletin. We need more bulletins here. So this is the double slit experiment in quantum mechanics. And there is some discussion about exactly whether every detail of this is right, but we think it's more or less right. And what's super interesting is that the full story of quantum mechanics and quantum field theory undoubtedly involves space-time. But it turns out that many of the core phenomena of quantum mechanics only depend on the properties of these multi-way systems. And so, for instance, the uncertainty principle in quantum mechanics, which is essentially operators don't commute, is a story of a failure of convergence of what we call branch pairs, what might be called, to theorem-proving people, critical pairs. And so, and what's interesting is in space-time, the analogous thing causes Riemann curvature, because you're applying sort of an X translation, a Y translation, and you're asking, does that XY commute? And that's a story of essentially uncertainty principle in space-time. The story of uncertainty principle in these multi-way graphs is the usual uncertainty principle. And but anyway, so in this case, what happens is, I don't know how into quantum mechanics you are, but one of the big things in quantum mechanics is the notion of quantum amplitudes, which are usually complex numbers associated with different quantum states. In our picture, it was a mistake for people to have packaged together quantum amplitudes into purely a notion of a single complex number. Rather, the magnitude and the phase actually come from different places. And so we think the magnitude comes from the path weights basically going through these graphs, and the phase is associated with essentially the position in branchial space that a particular state is associated with. The position in branchial space being essentially, if you were to think of this as a space, if you were to lay it out in this entanglement space, where does it wind up going? And anyway, in this case, we can kind of take a look at something which is sort of a model of the double slit experiment, and rather dramatically and amazingly, we get exactly the sort of expected behavior purely from looking at string rewriting, which is sort of remarkable. And we can, I mean, there's much more to say about this and sort of how it works and so on. But the basic bottom line is, the picture is these multi-way graphs are a representation of the sort of many histories of quantum mechanics. Completions are one way that an observer can instantly say, I'm going to observe this, I'm going to make an equivalence class of everything I think is the same, and that's going to be my sort of final classical observation. By the way, because of if the system is causal invariant, any completion the observer will do will eventually happen naturally. So in other words, the fact that their brain chooses to speed it up by imagining completions is not strictly necessary. It's something where the purely the course of time would eventually cause that completion effectively to happen, because the states, the future states of will merge. Okay, so why is this relevant to metamathematics? Okay, so the basic connection is, obviously you can think of something like this as being like a proof graph. And, to me, I keep on getting confused by this, and maybe you can help me out with this. But in this case, if I think about every edge as corresponding to the application of an axiom, I can say here, I can prove that AB is equal to AAA, and the proof would just be a path in this graph. In a different way of thinking about it, the nodes in the graph are axioms or propositions, and then we're saying, two nodes in more theorem prover-ish way sort of converge to make a new result. But so my goal has been to make a bulk theory of metamathematics. That is, usually in mathematics, you say, let's consider the actual theorems, and like, I want to talk about your lean math lib, which is an actual collection of, as I last counted it, like 36,000 theorems or something of that order. It's an actual collection of human found theorems. And so my question is, if I take the limit of all possible theorems and their proofs, what is that thing like? And then what is the geography of where humans have chosen to go in that space? That is, there's a geography, the space has a certain geometry, which I don't know how much we know about, trying to figure out something about it. And the space has a certain geography of where humans are populated. So okay, so as an exercise here, I had, I'll show you this very latest thing. As an exercise, I was looking at Euclid. So I had actually, back when I was writing my new kind of science book, I had this one mysterious note at the back of the book about empirical metamathematics, which was looking at the theorem network of Euclid to see what I could see from it. And this has sat here for 25 years, and I've been meaning to look at it again. And so now with my, let's actually try and understand, the large scale limit of metamathematics, I wanted to look at it again. So I can give you a quick view of what I found there. And then I want to, okay, so this is, let's see. Okay, so that's just the summary of what's in Euclid. Okay, this is the very boring, they're very boring things. Like, for example, that's the length of each proposition in Greek, the distribution of lengths in Greek and English. But it gets more interesting when we say, okay, that's the number of theorems referenced. So this is the distribution of the number of theorems referenced. And what I'm doing here is the different colors correspond to the different sections of Euclid. There's the 2D geometry section, the numbers section, the 3D geometry section. So they're purple, blue, green, as of today, at least. Let's see, this is just showing the number of theorems directly referenced in the standard Euclid proof. And this is showing, for a given theorem going down the books, this is showing what theorems it references. Actually, no, let me see. This is, right, so a theorem is going down the left, and this is showing that, what is this showing? This is showing that a bunch of theorems near the beginning of book 10 are referencing multiple other theorems at the beginning of book 10, for what it's worth. I really had never studied the detailed book structure of Euclid before about a week ago when I was doing this, but I now have a vague awareness of it. Okay, so that's the inter-book, inter-subject dependency graph. So that's showing that the extent to which the number theory books reference other things and reference each other, for what it's worth. And so this is now for a given proposition, this is now proving that proposition according to Euclid's proofs in terms of the various common notions and postulates. And then we can do the same thing. We can go a little bit further. We get these slightly more complicated things. This is a medium complexity proof in Euclid, showing the proposition at the beginning, chunk, chunk, chunk. Eventually, it comes down to a bunch of axioms here. This is various things about so this is showing, right, the total number of, this is what in physics we would call the past light cone of a given theorem. That is all the things that have causal dependence, on which that theorem has causal dependence in the proof graph. Did that make sense? So in Euclid, the theorem with the largest past light cone is the very last theorem in Euclid, which is the theorem that there are 5 Platonic solids. And we can make, this is a kind of messy graph that shows all in layers, all the theorems, starting with the axioms and ending with that 5 Platonic solids theorem. But anyway, so we can do all of this stuff for Euclid, and we can go and look at other properties of Euclid, et cetera, et cetera, et cetera. We can look at sort of what, I mean, the reason I'm interested in this is because I'm trying to make analogies between sort of things like light cones and causal graphs and event horizons and so on in the metamathematical space of proofs and in physical space. I mean, I'm curious, this notion of taking the sort of limit of metamathematical space, is this a notion that is somehow familiar in your world, or is this a totally arcane, bizarre thing?
Somewhere in the middle. I mean, people have looked at dependency graphs, but not in any very sustained or scientific way. So it's, it's not even clear how much it depends on the style of formalization.
Right. Yeah. Well, we might have some data on that, actually, because we were looking at lean and metamath just as examples of formalization things. So we might have some data as of about an hour ago, so it's fresh. Yeah. So I mean, but I'm curious about this notion of the thing that I'm most interested in is really taking this limit of the proof graph when the proof graph gets really big, and then trying to understand questions like, what are the interesting proofs in the space of all possible proofs? And I don't know whether that's now meanwhile, just to throw some more complexity on the story, Jonathan particularly has been interested in a very limiting case of this, which is in our multi-way graph, we are looking at we're looking for a given rule at all possible rewrites in the rule. We can also ask the question, what if we look at all possible rules? What if not only do we allow all possible rewrites, but we allow all possible rewrite rules at every step? And what happens then is we get these things which we call Rulial graphs, and I think I had written something about one of these. So an example of a Rulial graph is, where is it? Here we go. I looked at Rulial space in the case of Turing machines. So what's happening there is an ordinary deterministic Turing machine just chugs along and does its evolution, right? But a non-deterministic Turing machine makes a multi-way graph. That makes sense? Okay, so now we can ask for the extreme multi-way graph, the extreme non-deterministic Turing machine, the Turing machine that basically follows every possible Turing machine rule of a certain size. Make sense? Okay, so then we get a graph that shows where clearly many different Turing machine rules will wind up giving us the same states. So we get a graph that represents what we call this Rulial space. And we can look at all sorts of properties of this graph. And this graph has certain limiting behavior. For example, we can easily see that there's some group theoretic properties of this graph, et cetera, et cetera, et cetera. But we can look at the limit of this graph as the graph gets very big. It's representing all possible paths in this graph represent all possible non-deterministic Turing machine evolutions. Make sense? And we can ask ourselves someplace here, after a lot of nonsense here, let's see what somewhere I've got results here. Let's see, where do we go? Turing machine group, which is all very elegant. This is causal graphs, but let me find the big picture here that I wanted to find. Here we go. Okay, so that is a deterministic Turing machine evolution plotted inside the Rulial multiway graph of all possible non-deterministic Turing machine evolutions. So this is showing a particular deterministic evolution. If we were doing proofs here, you know, somehow non-deterministically, we'd just be saying, I want to get from one state here to one other state. If we're doing deterministic evolution, we're saying we're going to follow the exact same rule at each step, and then we get this deterministic picture. And we can look at things like, this is all possible, this is the points in Rulial space that can be reached by deterministic Turing machines versus all possible points up to a certain distance in non-deterministic Turing machine space. And so, I mean, but anyway, so why do we care about this? So one reason is the limit of this Rulial multiway graph seems to be an infinity groupoid of the kind that is the limit of higher category theory, you know, the Grothendieck type limit of higher categories. So
what are the higher cells?
Okay, so I can do one attempt, and then Jonathan will probably give me a better version of this. So in first approximation, the original paths, this is like some kind of weak category thing for the original paths. Then we can make the causal graph. So the causal graph tells us what the interdependence of these different rewrites is. So I could probably make, what is it, evolution event. What do I want to make, Jonathan? Evolution causal graph. So that's going to make something which shows, it's kind of a lousy picture, but let me do a few less steps. What this is showing is we've got the edges, the sort of the first level category edges, the one category edges here. And these are mappings between those edges, between those morphism-like things. And so that's the next level up. The next level after this, we interpret in terms of foliations of these graphs. Jonathan, do you want to say something about the way that the successive levels of categories work?
Sure, I can say something about that. So first, let me motivate a little bit why we think about them categorically at all. So one of the interesting things is when you take these individual branchial graphs, so a branchial graph for an individual multiway system, the branchial graphs seem to have, there seems to be some kind of monoidal structure involved, that you seem to be able to take monoidal products of branchial graphs in a fairly natural way, that actually you basically by composing the rules that gave you those individual branchial graphs together, you get some higher order multiway system that has both, whose branchial graphs are spanned by the two branchial graphs you started with. And you can show without too much effort that basically satisfies the axioms of a monoidal product. And so it means that there's some monoidal structure that is compatible between the branchial graphs, the multiway graphs, and the Rulial graphs, because the monoidal structure is coming in at the level of rule composition. And so there does seem to be some sense in which you can view these both the multiway systems and the Rulial multiway systems as being some kind of symmetric monoidal category. So the way then you construct the higher order cells, as you brought up, or these higher order morphisms, is so if you start from a particular multiway system for a particular rule, then assuming the multiway system is non-trivial and it bifurcates, then as Stephen mentioned, you can perform completions, right? You can basically, if you have two independent paths through that multiway system, you can map one path onto another. Just like, this is like a homotopy between paths in homotopy type theory or something. And the way you can actualize that in this discrete case of a multiway system is just by adding in pairs of rules that map from one point on a path to the other, to a point on one path to the corresponding point on the other path. I may have some pictures of that in this bulletin here. And then the point is, each time you add in those mappings, that's a new set of rules that a new set of effective rules that you're adding into the system. And then the Rulial multi-way system is what you get as the limit as you add progressively more of these completions, progressively more of these path equivalences. And so the higher order morphisms in this case are the second order morphisms are the rules you add that map not along a path but between different paths. Then those will produce new paths in this higher order multi-way system. You can then map between those and produce 3 morphisms and so on. And then the point is that the Rulial multi-way system is what you get in the limit as you add more and more of these higher homotopes. That's the basic idea.
And the reason why one might care is because of the sort of inevitable, the Grothendieck claim of inevitable geometry of infinity groupoids. And Jonathan has been pushing this idea that kind of the inevitable geometry of infinity groupoids flows back down to essentially inevitable geometry for things like space-time.
Or flows back up, depending on how you want to think about it. I mean, so one of the interesting points is that in our way of formulating fundamental physics in this model, things like the Einstein field equations for general relativity, or like the Wheeler-DeWitt equation for quantum mechanics, they emerge basically as...
Wheeler-DeWitt is confusing. That's a quantum gravity equation. The path integral, let's say, for quantum mechanics.
Fine, path integral. Although, yeah, okay, there's... Fine. Let's stick to the space-time case to be not so confused. But okay, so something like the Einstein field equation, they emerge basically as a consistency condition that's necessary in order for the causal network to have a reasonable geometry associated with it. That essentially, if you violate the Einstein field equations, that's another way of saying that either you don't have causal invariance, or your causal network doesn't limit to something that has some nice finite dimensional manifold-like structure. So somehow the emergence of geometry from these discrete structures, say in the causal network case, is intimately related to the satisfaction of the Einstein field equations. One of the reasons why, as Stephen mentioned, I think it's interesting that we seem to have this infinity groupoid structure for the Rulial multi-way system is because of Grothendieck's hypothesis that says that infinity groupoids and topological spaces are basically the same thing. And so what happens is when you fibrate the Rulial multi-way system to get individual multi-way systems, and then when you fibrate those individual multi-way systems to get particular spacetimes, the conjecture would be that that geometrical structure that comes from Grothendieck's hypothesis is inherited and helps to explain why, say, the causal network has a geometrical interpretation as a spacetime, or why the hypergraph has a geometrical interpretation as a Riemannian manifold, or whatever. It gives you a top-down view of why that happens as opposed to a bottom-up one.
So, yeah, I mean, okay, trying to relate this back to the metamathematics case. So I mean, one of our missions has been things like, what is the analog of Einstein's equations in metamathematical space? That's an example of a bizarre question. What's the analog of an event horizon? What is a non-constructive proof when fed back into space-time? These are questions that what are our foliations in space-time that correspond to reference frames in relativity? What do those correspond to in metamathematics? So we have hypotheses for a bunch of these things. I guess one of the things that might be of interest is, my little mission for the last couple of weeks, it's been longer than I hoped, has been to just get some empirical data from Euclid and then from Mathlib and so on. Okay, that's a foliation of that graph, and we don't have any better for those. Those are branchial graphs. Okay, since we given a particular kind of hammer, we have to use. I mean, we have to find nails. So these are branchial graphs that represent something a little bit bizarre. They represent the interconnections between theorems in Euclid at particular levels in this proof. So this is a sequence of proofs. We start from the axioms up here, and then we are making this, it's a partially ordered set, and we're making this layering of the partially ordered set, eventually getting down to there are 5 Platonic solids at the bottom. But we've got this layering here, and now we can ask at each layer, how are the theorems that occur at that layer related to each other? Related by common ancestry. And so this is their relation by common ancestry. And this is, I mean, again, it's not clear what the significance of this is yet, but this is showing if we were if we were a mathematician doing a breadth-first traversal down Euclid, this is what we would think the relationship between different theorems is. Now, realistically, a mathematician might do a depth-first traversal through Euclid. They might be, making a total ordering of this partially ordered set that makes a beeline for a particular theorem. So then they would get they would have a different set of foliations, a different notion of time in this, going through this proof graph. I mean, so part of the notion here is it's kind of the model mathematician, so to speak, modeled as a mathematician traversing the graph of all possible proofs.
And so remind me, common ancestor was direct ancestor, which is one step?
Yes. In this particular case, right. Go ahead.
And in the proof case, so this is, so A is a direct ancestor of B if B refers to A in the proof?
Yes, that is correct. Yes. And is that the right way around? Let's see. This is, yes. So I mean here, let's see what we can, let's get to the bottom line here. Okay, here's an interesting thing. We can look at, in this partially ordered set, we can ask what the effective dimension of this partially ordered set is. That is, we can start at a given node and we can ask what is the growth rate of the cone that develops from that node. So if this was a Euclidean-like space, then we'd ask for growth rates of balls in that space, and the growth rate of the ball would be like r to the d, where d is the dimension. In this case, it's a cone, so it's a t to the d like cone. And we can ask, not very interestingly for Euclid, although maybe we have an interesting result for MATLAB, for Euclid, this is the dimension as a function of distance in the cone, and it's pretty hard to tell what's going on here. What you see, I mean, when you do this in big hypergraphs that we're going for the purpose of having the universe, you see cases where the thing just sits at 3 dimensions over a large range of scales and stuff like that. Actually, we don't have great examples for 3 dimensions. We have good examples for 2 and like 2.6 dimensions and so on. But so there's a question of, does the thing limit, does the geography of metamathematical space? Because remember, this isn't really the geometry. This is just what Euclid chose to identify as theorems, so to speak. It's not some, okay, just zooming ahead here with what we do know. This is just amusing, difficult theorems in Euclid, blah, blah, blah. Most popular theorems, that's sort of interesting. Various kinds of ways to color that graph by popularity. You can do, okay, that's dependency graphs. Okay, this is just mildly interesting. You might find this interesting because I think you've worked on vaguely related things. This is how much the removal of lemmas makes Euclid less efficient. Okay, so needless to say, it takes a million. It takes 1.5 million applications of the axioms to get the most, the theorem in Euclid that involves the most machine code takes 1.5 million steps in machine code, so to speak. Even though as a, if you use lemmas, it takes, vastly less than that. Actually, I should make a picture here that shows, I should add to this table the case with, the case with how long these are if you do include lemmas, just to see what the compression is. Okay, and then this is about what super theorems you can add. In other words, what the most useful additional theorem to add to reduce the lengths of proofs is, which, I mean, in the Euclid case, and so it's not super impressive, but you can shorten theorems by a certain amount. Yeah, by 165 steps, you can shorten them. Okay, so we've had this big project. Okay, so this is about formalizing Euclid. Maybe I shouldn't talk about this. Maybe this is our attempt to make this sort of high-level language to describe Euclidean geometry. which we've gotten a fair distance with, and we can make these, we can do all kinds of things with it. Little different from really doing the lowest level, where we're explicitly writing down lowest level axioms. Those are Tosky's axioms at sort of lowest level. And okay, these are some proofs based on Tosky's axioms. This is an example just for the sake of seeing how things connect. So this is the very first theorem in Euclid, proved using our automated theorem prover in Wolfram language, find equational proof. This is the proof graph for that, where now those are the axioms at the top. That's the tautology down at the bottom. Then there are a bunch of critical pairs that are the yellow triangles here, and this is showing the interdependence of different, inside the automated theorem prover. And so it's not quite the same thing as the Euclid case, but what we, okay, I think I have a tiny bit more to explain, and then we're sort of finished with everything I know so far. So that's kind of how sort of the connection between the sort of very low level axioms of the kind that you can feed, an equational theorem prover, and being able to do Euclid type stuff, right? And so then another thing we can do is we can ask the question, in our multi-way system, imagine we started with the axioms of Boolean algebra, and imagine that we just generate all possible theorems using a multi-way system, using the standard axioms of Boolean algebra, right? We'll make a big mess because we quickly get just an immense number. This is the multi-way graph. We're just generating oodles of theorems of Boolean algebra, right? Okay, so the next question is, which of these theorems of Boolean algebra could we care about? And so I looked at this 25 years ago now. And so this is enumerating propositions of Boolean algebra. This is picking out which ones are actually true. And then this is, this is the true propositions of Boolean algebra. And then a big question is, of the true propositions of Boolean algebra, which ones will we bother to write down? And so this is the thing that in my big book was there are like 14 or so standard named axioms of Boolean algebra. And so what I did here was I looked at all possible true theorems of Boolean algebra, and then I'm marking which of the theorems anybody bothers to give a name to. Make sense? So the really big surprise, as far as I was concerned, was that I had thought that this naming would be purely historical. But there is a procedure, it seems. With this ordering of possible theorems, the ones that were given names seem to be the simplest instances of things that cannot be proved from things earlier in the list. So for example, if we just go through that list of theorems, we say, so I'm showing it in yellow if it couldn't be proved, and then I'm showing the proof graph if it can be proved from something which precedes it in the list. And so the surprising claim is that the theorems people bother to give names to are the theorems that are the first statements of new facts about Boolean algebra. And obviously, eventually you run out because you've got something equivalent to the axioms. Okay, so the result as of just an hour ago or something is, let's see, where do I have that? I need to pull this up. Did I have this here? Oh, here we go. This is what is this now? Okay. Well, actually, this is, how to explain this? This is basically showing, this is the analog of Euclid for Boolean algebra. Boy, this is only an hour old, so I'm not as well equipped to explain it as I might be. But let me try to say what it is. Okay, so I found these very simple axioms for Boolean algebra 20 years ago. Right? Minimal axioms for Boolean algebra. The absolutely minimal axiom for Boolean algebra that I found has a hard time proving. So these theorems are given in terms of and or, not but we can map and or not, obviously, to NAND. So in terms of NAND, those theorems become a little bit longer. We can then ask, how do you prove from my single axiom for Boolean algebra, how do you prove those theorems? We prove them in the automated theorem prover. I've actually never seen such a long proof from the automated theorem prover. There's a 1500 step proof here that I guarantee is incomprehensible. Anyway, they're hard to prove from my one axiom system. I had a two axiom system, which also includes commutativity. That makes them much easier to prove. In terms of the two axiom system, let's see, this shows the intermingled proof graph of all of those theorems. Okay, so what does that mean? That means we're taking all the proofs of all those theorems and we're making a graph union to show the interdependence of lemmas between those different theorems. So the things being proved are the yellow dots. And this is showing basically the analog of Euclid in the sense that here are the things that we care about, the yellow things, the things we care about. And this is showing which lemmas and what the relationship between lemmas to prove the things that we care about, if that makes sense. This result, this is the actual dependence based on the automated theorem prover of the theorems that we thought were interesting. So in a sense, we're kind of channeling Euclid here of saying, ignore the lemmas in between. Actually, Jonathan, you just made this picture, so I don't actually know what this is. What happened to the intermediate lemmas?
So the directed edges are corresponding to when there is an overlap between the intermediate lemmas and the theorems that you care about, right? So it's saying if in the proof of theorem A, if there was an intermediate lemma that is equivalent, that is sort of immediately equivalent to the statement of theorem B, then draw a directed edge from theorem A to theorem B. So
if a theorem that you cared about happened to show up as a lemma,
yeah,
then indicate it. Is that right?
Exactly. Yeah, right. But don't show any of the other lemmas.
Okay, so this was an automated Euclid, so to speak, with an additional "do we care about this theorem" thing added to it. So in other words, this could have been just go find the distributive law down at the bottom here, and you find a bunch of intermediate things. And the question is, did you chance upon another theorem that's interesting? But okay, so this was the Euclid thing. So now I wanted to do the same thing. Okay, somebody on our live stream is asking, is a single axiom for Euclidean geometry possible? It's certainly a very complicated one, is certainly possible. But whether there's a simple one is a very good question. I am most curious about that. Okay, these aren't very interesting. These are, well, they are interesting, but they're not relevant for our discussion here. They're the structure of topology in our thing. So this is, okay, so here, this is more familiar. So this is from MathLib. This is Pythagorean theorem. And this is showing, those are the direct dependencies in the quoted proof of the Pythagorean theorem. This is Euclid's version of the Pythagorean theorem up here. This is the proof in Euclid, and now the proof in Lean. That's the full proof, if I got it right, in MathLib and Lean, where we're starting off from. Oh gosh, which way up is this thing? I think this is theorem at the top going down to the things that are needed to prove it at the bottom. So this requires more analysis, but this is basically, that's the analog. So this thing involves about 2,800 elements. So that's basically showing if you want to prove Pythagoras' theorem from first principles in Lean, that's the sort of the graph that you get. The analogous thing in Euclid, much simpler because it's being much less rigorous. It takes, I don't know how many, I'm sure I said how many, 39 nodes in Euclid, which translates to 2,800 in Lean. And our initial estimate for MetaMath was, I think 8,000, but I think we discovered this morning that we got that slightly wrong because we included some stuff we shouldn't have included. So I think it's going to be more comparable to the Lean result. Does that surprise you? I mean, I'm curious what.
Surprised me what, that it's so large, you mean, or so that
Well,
that
I'm
they're
just curious,
similar,
A, that
or?
it's comparatively large, B, how it would compare to MetaMath, or any other comments about this.
No, I'd have to think more. So again, so tell me what. So this is this is the same game that you played with Euclid and the Boolean, that you're doing dependencies, but you're filtering out, or you're just marking certain ones that you care about along the way.
No, we don't know which I mean, you've marked the ones you care about in a sense,
Oh, I
because
see.
you've
Okay.
only defined certain theorems to be in MathLib. That is,
I see. Okay.
right? I mean, given the axioms, there's a gazillion theorems that you could have proved, right? So we're not answering. So what this is geography,
Okay. So this is just a
not
report of
geometry.
what's in the library.
Yeah, right. So among the questions are, there are a couple of questions. To what extent does geography imply geometry, so to speak? That is, from what's in the library, what can we deduce about the structure of the mathematical space as a whole? To what extent, given that we know features of the geometry, what constraints does that put on the geography, so to speak?
Yeah, I mean, I suspect that most of the structure there is just the construction of the real numbers and properties of the real numbers.
Okay.
Because it looks like you're just using norm space. I mean, proving the Pythagorean theorem for axioms for a norm space, and and basic property of the real numbers, I think is pretty short. I think I think the work is just constructing the real numbers from from
Okay.
Cauchy sequence of rationals and so on.
Cool. Well, we should see that, because so long as we can figure out how to tag different sections of MathLib, then we can color this graph by because, for example, if we look at Euclid, we can see in those Euclid pictures, we can see what's being exercised. In fact, we should do that for the Pythagorean theorem here. We can see in the Pythagorean theorem, actually, I should remake this picture with better, here, let me remake it for a second. With bigger, so that we can see it more obviously. And let's see whether Euclid is messing around with numbers in his attempt to, let's make vertex size 2 here. Okay, so this is now Euclid's version of proving, oh no, that this is all living in the 2D geometry section of Euclid. So it didn't go into the numbers section of Euclid. Possibly because Euclid doesn't really have.
The Pythagorean theorem?
Yeah.
No, the Pythagorean theorem is just the end of book 1.
Right, exactly, 1.47. Yeah. Right, so okay, so then your claim is that that in the case of lean, what it's doing is basically it's wandering around constructing the real numbers as, see the thing I'm trying to understand, if I try to understand mathematics in bulk, so to speak, you say, okay, there's constructing the real numbers. That's a big sort of freeway that you could build a big freeway that's associated with making real numbers. And then there are lots of kind of surface streets that you can get to fairly easily from that. And I'm just trying to sort of understand how to think about this process, how to think about the advance of mathematics in terms of how it colonizes mathematical space, so to speak.
Yeah. Well, so here are two thoughts. I mean, so when you build a library, you construct the real numbers, and there's a lot of dirty work that goes into Cauchy sequences, and all the low-level properties, and then you show that they're an instance of an ordered ring, an ordered field, and so on, and then you throw away all the stuff underneath. You just use that interface. So there's in the library there's certainly a modular structure, so that if you later change the construction of the reals, it doesn't break the whole library. I mean, everything goes through the interface. So one question
should appear in this graph. That should mean that there is a throat in this graph, so to speak.
That's right. So somehow there should be So yes, the first question is whether you can kind of see that modular structure. It should,
right.
It should. And then the other thing you might want to do is, okay, so now factor it out. Now look at what the graph looks like up to,
Exactly. Right.
Yeah.
Right. So in other words, you're saying, let's imagine that I just make an equivalence class of all things about real numbers here that were in the real numbers section of the MathLib library.
Yeah.
Then make that a single node, and then ask how that relates to the other nodes here.
Yeah, at the extreme, or at least, or you just take again the defining property is that it's a complete ordered field. So maybe that's 20 nodes, but maybe you isolate those 20 nodes or something like that. And so yeah, but even collapsing them all to one, that would, I mean, yeah, that would be perfectly reasonable.
But you see, I mean, to me, that's an interesting statement. I mean, if you imagine what this graph looks like, imagine mathematics 1,000 years in the future, when we have, who knows what's happened to mathematics then, but the limits of mathematics as t goes to infinity. What does this graph end up looking like for the theorems people care about? And to me, the it's and so, well, okay, so actually to ask one really practical question, to extract the area for lean, is there an easy way to do that? I mean, from MathLib, I think we had a, what was it?
Well, there's a file structure. So, things are grouped into files, and files have dependencies.
Okay. So in other words, if we take, I think James was untangling this. And did we manage to get this? Okay, so you basically say that
roughly 1,100 files that the theorems fall into, right? And so I guess we need to decide on a level of granularity.
Yeah, I'd be happy with like 15 areas.
Open mapping, is that Banach spaces or is it analysis?
No, it should be analysis. I mean, we want like 15. I think.
Well, on top of that, though, I mean, so the files in the library, the files are divided into folders. I mean, there's, the users have, so there's a user-defined folder hierarchy that might be helpful to you.
Right.
And then another piece of information is that there's another hierarchical organization into namespaces. So if you look at the identifiers, there's, algebra dot whatever or real dot.
Right.
So theorem names. So that's also information that may or may not.
Is that consistently done?
No. So it's really kind of ad hoc. It's, it's as users, it's when they, I mean, it's considered bad form to put everything on the top level because then you can't reuse a name and so on. So, so lots of things are in maybe one namespace deep, but how to divide things up and how often, and again, there's no, it's really up to the library designers. There are no fixed rules.
This is, this may not be yet correct, but this is the distribution of numbers of theorems directly referenced in a given theorem in lean metamath and Euclid.
Yeah.
I don't know. Don't count on this being correct. By tomorrow, it might be correct, but it isn't. It's not guaranteed correct yet. Yeah. And this has
by the way, it occurs to me. So I do. So I still don't have a feel for the for these branchial. What were they called? The
branchial graphs. Yeah, in American it would be branchial. Sorry, I'm
right. But certainly the dependencies are certainly very natural to study. I mean, one way it's very relevant is so for automated theorem provers, they rely on these sledgehammers. You're trying to prove a theorem, and some heuristic filter goes through and sort of extracts a bunch of lemmas, and then you just throw a resolution theorem prover at it. But the way, so look, there's a lot of redundancy in the library. You have theorems A, B, and C, and you use them to prove D and E. And so, the filter might pick up, D and A and B, even though D follows from A and B. I mean, you'd really, the question is, what you'd really like are sort of more useful or more meager, more, what's the word I'm trying to say? So sort of less haphazard, more carefully chosen, more curated collections of facts for your theorem prover to use. And so the question is, if you want to set a theorem prover, if you're just, trying to prove a random goal and you're trying to set your prover loose on it, is there some skeleton to the library that you want to focus on rather than just, potentially throwing the whole library at it?
Right. Well, I mean, and also, in my surprising claim from Boolean algebra that there is a machine executable way to find out which theorems will be considered interesting, that would allow you to basically go and explore, a much bigger space without any humans involved in building a library. You just go start generating theorems. And if you have some good criterion for interestingness, then potentially, and again, that picture we were just making that showed the use of different lemmas in the proof of the interesting theorems, because presumably what you care about, okay, so there's a geometric question of what theorems are the most useful kind of milestones in proving everything. And then there's the question, which theorems are the most useful anchor points or milestones or whatever in proving the theorems you care about. And those might or might not be the same answer.
Yeah.
And so, do you have a sense? For example, for the first of those, if you just look at all possible theorems, do you have any sense? Well, actually, for either of those questions, what are the useful?
No sense at all. The first question, it seems to me that it could very well depend on, sensitively on, what your choice of language is, what your choice of,
yes.
are you just starting from, set theory with an epsilon relation, or, so I don't know.
My contention would be that it does not depend on the language. And my contention is that it's like, what we think about physics is that tons of facts about physics, in particular relativity and quantum mechanics, don't depend in detail on the structure of the underlying rule. They depend on certain global features like this causal invariance property, but they don't depend on the details of that underlying rule. And so why that motivated this investigation of mathematics, because what if we could do the same thing in mathematics and have global results about mathematics that don't depend on whether you're using set theory, whether you're using, some other foundation for mathematics, but are generic results. So for example, one possible, one thing we were playing with was, okay, so one contention, which I would say is as yet just a contention, is that non-constructive proofs lie on the edge of essentially metamathematical space before you hit event horizons. This may not be correct, but we have sort of a possible way of thinking about models as being related to foliations in metamathematical space, and the failure of foliations associated with, again, some hand waving here because we're not sure, but that's the type of results. The question is, one question would be, if you wanted the analog of Einstein's equations in metamathematical space, what would that do for you? In other words, if you could say, so a GD6, so Einstein's equations are all about GD6. It turns out the path integral in quantum mechanics is all about GD6 as well. In these proof graphs, GD6 are, the shortest proofs of theorems, presumably. And, the mathematician doesn't, neither the mathematician nor the automated theorem prover probably gets that close to the shortest proof. But nevertheless, maybe it's a good qualitative model. And then Einstein's equations would tell you things about the essentially deflection of shortest proofs by the presence of energy, which, again, this is a stack of ideas here, okay. The contention is potentially the analog of Einstein's equations is something about the number of lemmas that are relevant to making further progress in a proof determines the extent to which the geodesic of that proof is deflected. In other words, it's like when you have more mass of lemmas, your straight line, that the lemmas represent a massive object that basically gravity is pulling the geodesic around that pile of lemmas. That's a very qualitative picture, but the question is, one thing we'd really love to know is, if you were going to make a global theory of mathematics, what kind of a thing would it say? So for example, this might say, for example, one of the things that would be lovely to prove is the analog of the singularity theorems from general relativity for metamathematics, which would be some kind of inevitable, so decidability is the analog of, probably the analog of a space-like singularity of the kind that occurs in general relativity. It's a thing where essentially time ends, everything, you get an answer for everything. And so, there might be some result about the fact that when you have built up enough lemmas, there's some inevitable singularity that occurs, something like this. I don't know. I'm just curious. Does this resonate with anything that people have studied in your kind of world?
Oh, not that I know of. So I have very little feel for the physical interpretations. What's the first place if I want to start trying to get a sense of the physical interpretations you're telling me about? Where's a good place to look?
We have this whole website about our physics project, and probably the best thing. Now I'm gonna sort of guess at the optimal thing for you in particular, okay? Because there are different entry points. So the somewhat non-technical entry point is this announcement post I made. If you want something more mathematical, I recommend Jonathan has a couple of papers about relativity and quantum mechanics.
Oh, good. Okay.
And I have a long technical introduction, which requires less sophisticated mathematics, but has more pictures. And then more recently, I've been saying to Jonathan, it's possible nobody will understand this paper for 100 years. So if you read it and understand it, and give comments on it, this is Jonathan's first cut at something about this higher category theory business, and that's but the thing that the thing right now the main thing that I'm just I'm just curious, and I know you have to go in a moment, but I'm just curious whether like the study of the limit of metamathematics does that resonate with anything, or is that just like bizarre? And
no, I haven't heard anything like I mean people have looked at dependency structures of libraries and so on, but
mostly like code bases. I mean, thinking about the more like sort of code based dependencies. Is that right? Or
that's right. I don't know of anything.
What have they concluded from that? I mean, I've seen pictures, but I'm
I don't know. I mean, I know people have looked at it. I don't know.
Yeah, I'm not sure there's been. I mean, I think to ask an unfair final question, perhaps. I mean, as we look at all of these great things that have been done in MATLAB and Lean and so on and so on and so on, the question part of the question I'm asking myself is, we have our whole Wolfram language technology stack, and it's off in a slightly different direction. And the question is, how can we use all this amazing work that's been done? And we're really struggling because we're trying to figure out, we've now got pretty decent equational theorem proving in Wolfram language. We've been making a collection, we've been making this collection of axiomatic theories. This is about to get much longer. These are just collections of, I don't know, let's pick some I don't know what, this just as a, we're just collecting, axiomatic theories and notable theorems and so on. And this is, but I mean, and we could imagine, collecting tons of theorems that exist in MATLAB, for example, in the same way. But the question is, what would you do with them? I mean, what would do you imagine that for example, one obvious question is theorem search, which seems very hard. And it seems very, I have this, this vague idea that our story about Rulial space is not completely unrelated to theorem search, because it all has to do with making these transformations, which are essentially given two theorems, are they actually the same theorem? And we have the same issues in making sort of coordinatizations of these spaces and so on. But so that's one thing, is theorem search. But I'm just curious whether you have an immediate reaction to kind of what, if we're trying to think about sort of how do we make, I'm looking at all the stuff that's in things like MATLAB, and it's just so much stuff. And it's surely there's a way to use this.
For me personally, I'm a pragmatist, so I care about theorem search, theorem search and discovery. So that's that's what is of greatest interest to me. And one thing that's going to be hard about studying the graph is that, the question of entailment is it's undecidable, right? So the question does,
Right.
does this follow from that? So you're almost forced to rely on, rules in a specific calculus. You can say whether this follows from that by, one of these 6 rules or something like that.
No, but that's a point of view about mathematics. I'm not sure I necessarily. I mean, that's an ultimate truth point of view about mathematics, because in my multi-way graph, it just does what it does, so to speak. I mean, that is the presence of undecidability is just the statement that there are paths in this multi-way graph that can be arbitrarily long. In other words, if you right, and in fact, one of the things I think is interesting is one of the surprises to me has been that when I do kind of experimental mathematics, just sort of, going out in the computational universe, finding some system and trying to show things about it, it's often the case that what I end up with is undecidable. Yet, working mathematicians do not run into undecidability all that much. And so one of the things I've long been curious about is, why is there this difference? And I think this kind of thinking about metamathematics gives a way to think about that, because the claim would be what you are doing with MathLib, or potentially what mathematicians in general are doing, is they're building out this sort of road network of things that they can prove, and things that, whereas when I just jump, and that means that you never get into, when I just go out in the computational universe and do a random computer experiment, I'm jumping to some random node in this giant graph. And then the question is, can I connect that random node in the giant graph to some other node that, that represents a tautology or something like this? And that will often be undecidable. Mm-hmm. But, there's an arbitrarily long path. But nevertheless, in this build out that, mathematicians are doing, I would claim the reason they're not running into that is because by the very construction of their enterprise, they're basically building out the roads as they go. And so they're never off in the jungle without any roads. I mean, does that seem plausible, or do?
Yeah. Well, but so then the other concern is that just the combinatorial, being overwhelmed by the combinatorial explosion. So you can start to explore all the things you can get with 1 step or 2 steps or 3 steps, but 99.99999% of the things you get with 3 steps may be just uninteresting. Right. So whether you can sort of automatically.
Right. So how far away are the interesting theorems, right? So this was the thing, like 20 years ago when I was looking for the simplest axiom system for Boolean algebra, the big surprise is the simplest axiom for Boolean algebra is the 50,000th axiom. It's not the quintillionth possible axiom. It's the 50,000th. So, but then, I mean, that's a great question, is in MathLib, for example, if we enumerated all possible theorems, how far out are the ones that you have chosen to populate MathLib with, so to speak? And you're, but the reason that I'm not afraid of this, absurd combinatorial explosion is because I think that's what happens in the universe, and we manage to make a bulk theory of the universe even independent of that. That is, the current estimate might be that there might be 10 to the 500 sort of atoms of space in the sort of multi-way graph of the universe. So 10 to the 500 is a big number. It's a big enough number that, so far as we've been concerned for the history of mathematics, space is continuous. But in actuality, it's probably not. And so, in other words, but the whole point is the big excitement of physics is that even though it's 10 to the 500 little crazy little things with all kinds of connections between them, there are bulk things we can say, like Einstein's equations. And so that motivates the idea that maybe there are bulk things one can say in mathematics that transcend, but mathematics is a different case, because it's like, okay, so my claim is that this, wherever it is, wherever that picture was of MathLib, this is like exploring the solar system. That is, there's a geometry underneath this, and this shows the actual paths of spacecraft exploring the solar system, so to speak. They're the places where we've chosen to go, or you've chosen to go in building this library, as opposed to, and there are probably statements to be made about, the question of where you can go, no doubt depends on, the gravity well of the sun, so to speak, as well as where you choose to, go because it seems like a cool, planet to explore type thing. So I guess this is the, the question is are there underlying statements that can be made about the bulk structure of mathematical space? And then are there kind of meta human statements to be made about where people choose to explore? And I mean, what would be your guess? I mean, if you were going to guess of all possible theorems, which ones do mathematicians go for? Which things do they build? What kinds of, would you have any kind of qualitative characterization?
Oh, it's hard because, ultimately, things relate back to experience, to, our experience with space, our spatial interactions, counting, things we care about,
Right.
And then they just kind of branch off from there. So it doesn't start from a mass of disordered things, and it starts from things that are physically meaningful to us, and
right.
goes from there. So
by the way,
yeah.
I think one of the conclusions of our physics project is the fact that we think of space and time and all these other things in the way we do is not necessary. It is not the way the universe is. It is merely our particular description language for the universe. And we could have an utterly incoherent description language. And it would be, in some ultimate sense, equivalent, but it would be kind of so this statement that mathematics is the way it is because physics is the way it is, I think is not correct. In other words, mathematics may be the way it is because our perception of physics is the way it is, but I don't think it's true. I mean, it might be true, but I think there's a science question whether that's actually true or not. But I think it is not true. That and so I think the so for example, if we think about models of things, I mean, you talk about the real numbers and you talk about, okay, so one thing we imagine is that in these proof graphs, that the foliations of the proof graph are related to models. In other words, what you're doing effectively is to coordinatize. When you make a model, you're effectively taking that proof graph. I'm not sure if that's, I'm curious whether you think that's a reasonable intuition. When you make a model, you're taking a proof graph and you're effectively coordinatizing the proof graph. Does that, in other words, so oops, wherever I have it, if I take some random proof graph, and then I'm saying, now I'm going to identify these things. I'm going to say which of these is at which coordinate position, so to speak. And that's kind of the analog of picking a particular model. Does that ring true, or does that seem?
Oh, so it's sort of interpreting the proof in a particular model?
Yes. So basically saying, if I take these as being words effectively, and I've got my concatenation operator here, and I say, I'm going to assume my concatenation operator is this particular thing, that will sort of put every one of these strings at a particular coordinate position. And that will turn what here is defined by the proof graph as a partial ordering. I will just have a total ordering of these things based on the evaluation of them. Maybe Jonathan has a better way to say that, that's more mathematically sound.
Well, okay, but the way I would just formulate it is that, the first incompleteness theorem tells us that sort of semantic truth is model dependent, right? Or in any sufficiently rich axiom system, semantic truth is model dependent. And in relativity, we have this concept of Lorentz symmetry that tells us that the ordering of space-like separated events is gauge dependent. So in other words, space-time defines a partial ordering on events, doesn't define a total ordering. There's still some gauge dependence on what total orderings you can see. And then the large-scale conjecture is that the two things might be related, that effectively what's happening is proof theory defines a partial order, model theory turns that into a total order that's consistent with that partial order in a manner that's analogous to making a gauge choice in relativity. And
yeah,
so
that seems like a reasonable analogy. On that note, I should really go. I have to teach
well, thanks
just
for
a little
joining
bit.
us.
Thank you. I've enjoyed it very much.
Okay. We'll have to do it again. Right.
Okay.
Thanks.
Bye-bye.
Bye. All right. We should probably wrap up ourselves in a moment here, but maybe we can just go through a few things that right. Yeah, it's probably a longer discussion to look more at these graphs and to try to understand what's going on here. I mean, it would be interesting to know what the lengths. I mean, I was actually about to label this thing. Hold on, let's just do that. I'm sorry, I'm just too curious what this actually is. So which theorems occur at which points in this picture? So let's do the following. Let's say here, vertex labels goes to, hash goes to, if, which ones are the yellow ones? How do I tell if, oh, if member Q, what is it? Propositions? Is that what? If member Q propositions hash, then I want to do automatic. Otherwise, I want to do none. And I want to map that over dependency network and over vertex list of dependency network. And if this generates picture, oh, come now, what's it doing? Oh, there we go. All right, now we're about to find where those axioms of, where those results of logic live. Oh, come on, they're all scrunched up there. Help, I can barely see them. All those lovely results of logic. That's, let's do the follow.
Don't do a layered digraph embedding. Why not do a spring electrical?
All right. I was going to, I was thinking I would just make the, all right. Now, why has this got an incoming edge only from that theorem? All these theorems have incoming edges. Why is that?
What do you mean? They all have exactly one outgoing edge. They're all hypotheses in the theorem prover, right? So they go into a conclusion.
Oh, theorem provers drive me crazy. They're all backwards.
But no, that makes perfect sense. You want to prove that a proposition is true.
Okay, so is that true in the middle there?
No. I think the purple is true, Mano. I think, right?
Yeah.
Purple is true. So
yeah.
everybody's going there.
Yeah. So if the theorem is correct, there should be a path from the yellow thing to the purple thing.
Okay, so why are there direct paths from these theorems all just directly to purple? That doesn't make any sense.
Well, that's what I was talking about at the beginning, right? So in most cases, what the theorem prover is trying to do is build up enough substitution lemmas and critical pair lemmas that the proof of the theorem ends up being trivial, right? That you can just use some previously proved lemma to immediately reduce the hypothesis to true.
But why aren't we seeing that in here? Why aren't we seeing it go through the intermediate lemmas?
No, but it's not going through the intermediate lemmas. It's using the intermediate lemmas.
But why isn't there a node in the proof graph, in the theorem prover proof graph? There would be an,
there would be a dashed line
for the usage.
For the usage, as opposed to a solid line for the transformation.
For the substitution. All right, so we need a version of this which shows usage, because the analog of Euclid is usage. Right, Euclid is describing how he's using a previous lemma.
Yeah, although I suspect he will. Okay, if Euclid is characteristic of normal mathematical writing, there'll be an awkward combination of both, because sometimes people will say, using lemma 3.16 or whatever, but then sometimes they'll also say, starting from the statement of theorem whatever, show this. And
absolutely.
People interchangeably, but that's not
so. So Mano, here's the thing we'd love to have for this picture. Let's have both. Let's have dashed lines. Let's have two kinds of lines here: the substitution lines and the dependency lines.
Well, if you're going to show that, you don't you might as well just use the output of the theorem prover. You might as well just ask the theorem prover to prove all the things in toProve using the axioms, and just use and just get the proof graph out of that. You're going to be generating the same thing.
So can it do that? Can it prove all the, you're saying?
Yeah, and it will show those as being separate hypotheses.
Okay, so if we say in here, so you say, if I go here, it says there are propositions here. Is that right?
And if you want to put it into find equational proof, you should use to prove.
Okay. Where is to prove?
Propositions doesn't have quantifiers, right?
No, it
Okay,
doesn't.
all right, okay. Okay, so let's say here, we're saying to prove, is that right? To prove is, that's, okay. And now where are the,
Those aren't quantified either.
what's that?
Those
One
don't look.
sec, let me check.
Those look okay, aren't they?
Those
Those are my interesting theorems.
Yeah, but like I say, they're not quantified, so it's dangerous.
Ah,
You don't know, like if you put them into find equational proof, it's anyone's guess whether it's going to treat them as being constants or variables.
I think it shouldn't be anybody's guess. I think we should make that a deterministic thing.
Well, no, okay, I mean, it will treat them as being what they are, which are constant literals. But in the context of the theory you're proving in, whether that's equivalent to treating them as variables is not deterministic.
Right, okay.
So S theorems in Mano's document looks like it's the right thing to use.
Okay, fine. Okay, so then
You want to use S theorem, you want to prove
S theorems from what was the collection of things, Mano? What's the collection of things to prove it from?
is it full cats?
So yeah, I think so. It's yeah, Wolfram commutative axioms with the ancillary definitions.
Okay, so full CACs. Okay, drum roll. Let's see what we can do here. S theorems using full CACs, right?
Mm-hmm.
Wait. Is that
Yeah.
right? Why in this? Sorry, I'm just looking through the Euclid blog items. In the definition of notable proofs, you're using to prove rather than S theorems. Is that so? Maybe you should use.
Yeah. Should we have quantifiers for the propositions?
Yes.
Okay.
By the way, Manu, these are not in the correct order. And they're very weird list. What is this? I don't even know what this list is. This isn't the standard list of notable theorems, is it? Certainly not in order.
I got it from the draft.
No, but that's a different thing. That's a different thing. That was a list. Well, let me see. While it's running, we can do that. We can take a look. So that's those. And then,
Oh, did it complete?
hold on. Okay, that's the list of interesting theorems. That list there is the correct list.
Okay.
Okay, so that list has to be packaged to be, no, it did not complete. But okay, so you say that that will show that it will try and combine paths as much as it can. Is that right? Jonathan?
Sorry,
As it tries to prove all the, I mean, this is an overproof, so to speak. It's too many things there.
Right, yes, but right. It will combine anything it can combine.
Right. Okay, so then you're claiming that that will show, that will be the sort of faux Euclid. And then you can ask the question, for this graph that you made here, what is the interdependence of different, in what way was one of those theorems used in order to prove another one? Right?
Right, exactly.
Okay. And
Well,
fair enough.
I just checked that all of them, they all can be proved independently, and I've succeeded in proving some smaller subsets, but clearly doing the whole thing is.
Well, but even if one didn't, if one did them independently, couldn't one just do this graph union thing that Mano was doing?
Yeah, no, exactly. But my point is that this is just going to be doing the same thing, right? What all you're going to be doing is reconstructing.
Right.
Proof.
Well, it doesn't help that I'm going to stop this because this is computing slightly the wrong thing. And Mano, if you're able to try and compute the right thing, that would be terrific.
Sure.
And so yeah, just a summary. So what we've learned from I know we have to up.
Sorry,
is that right? Is that all that you need to do?
No. I'm just saying as an example of what I meant. So the point is that the advantage of having the actual proof graph is that the equivalences between intermediate lemmas are computed implicitly. Right. So if you request out the proof graph for that, it will have each individual hypothesis.
So the hypotheses are
those dark green things.
The dark green things here.
Yeah. Right.
Okay, dotted around. These things are the axioms.
Right.
Okay, so this is the analog of our Euclid.
Mm-hmm. Right.
Why are there two conclusions here?
What?
Oh, there's a conclusion for every hypothesis that got proved.
Right. Well, each hypothesis is treated as a.
Isn't it cute that we made these things look like QED markers?
Yeah,
that was not coincidental.
That was not.
It was not coincidental. It was a good idea. It was coincidental, maybe, that these, critical pairs look like branch pairs. Okay, so this thing then, yes, it's sort of the analog of the Euclid case. Yeah, it's a little different because it's saying really that what we should do is replace those conclusion markers. We wouldn't show the hypothesis. We would merely show, no, I'm really confused actually. All these conclusion markers, see, Euclid doesn't have that same kind of structure, right? Because it doesn't show the, yeah, okay, well, anyway. Cool. By the way, I thought it was interesting. I was interested that Jeremy thinks theorem search is the top priority in terms of what to do with these big libraries. I think that's very interesting. I think it will be worth understanding, what do we learn? Okay, my final question here. What do we learn from the study of metamathematical space about the theorem search problem? That is partly a Jonathan question. That was not a rhetorical question. I mean, in other words.
Yeah, sorry, go on.
Well, no. I mean, the question is, look, if we could know, yes, here's a good question. This is a good question. If we could populate metamathematical space with the interesting regions, if we could say where's interesting in metamathematical space, then if you're plopped into the middle of metamathematical space, the question is, can you find beacons around you? Right? That would be one example of something that you might be able to do in sort of the continuum limit, is to say, where are the interesting theorems that are near me? Where are the theorems that some criterion would consider interesting that are near me? Unfortunately, there's a very high probability you'll be dumped in the ocean with no sign of land anywhere nearby. And I guess the question is, what can we learn about the process of searching for theorems by knowing the structure of the space?
I'm not fully sure I understand the question. I mean, of course, knowing what things are near to other things helps theorem search. I don't see how it couldn't help.
Yes, well, right. But so if we have a branchial structure for theorems, that's interesting. So the claim would be, could we search for theorems by searching branchial space? If we knew how theorems were related in branchial space, could we use that as a theorem search mechanism?
Right.
So in other words, if we knew how theorems were related on the proof graph, could we use the interrelationships implied by the proof graph to determine, the most interesting thing is, given a theorem we've never seen before, what are its coordinates? Right? Now, interestingly, with space, I don't think you have a chance of being able to answer that question. In other words, if you're just given a piece of space and asked, where is it? I don't know how you specify it. I don't know, if you were given a little lump of hypergraph and told, this is a part of space, where is it? Good luck in figuring that out. Seems hopeless. So, yeah. Oh, yeah. So Rory on a live stream is saying, could we add we do have that, right? We have a weighted proof graph thing, don't we? Let's do that, actually. That's a good thing to do. I haven't been using those much. Is it called proof graph weighted?
Yeah, there's a proof graph weighted, but what was the question?
Oh, it was a question on the live stream about visualizing, about making it easier to understand what's going on in this picture. Oh, that's interesting. It's using a centrality measure, right? Some kind of betweenness.
Looking at the betweenness centrality of each lemma and then resizing the nodes according to it.
Oh, that's a good idea. Because that way, that is sort of the analog, because I did the betweenness centrality for Euclid.
Right. So in other words, it's saying how critical were these lemmas in proving subsequent results.
Right. Well, super interesting. All right. We should probably wrap up here. And thanks to everybody for joining us. And thanks to folks on the live stream. And I at least found today interesting. So hopefully other people did too. And until the next time, see you all